Okay, welcome to Sir Majesty's World Science Channel. Today I will handle NECO Chemistry Paper 2 2021. We just concluded ones, you see here. So we're going to be looking at the Paper 2 questions. So let's go and lift the questions. These are the ones we answered. Okay, this is 1, 2. I'll start from number 6, then from 6 I'll get to 1. Remember to make your contributions where necessary, for 2 good heads are better than 1. Then take corrections where necessary also. So over here, the question number 6 says, draw a well-labeled diagram for the laboratory preparation of sulfur 4 oxide and mention the catalyst used for the following reactions and explain its effect on the system. Okay, so this is question A. So I will be as fast as possible, but also try to be accurate. Then pardon any of my minor errors, but I promise I'm going to try to be perfect the much I can. Yes, but with your help also. Okay, so I will just see the safe preparation of sulfur 4 oxide. Let me get my answer. So here I have to lift this question, maybe to help if I can. But since we have it, these are all photos, so I'm not seeing. Okay, so I think we're there. So this is the question. Yeah, I have to bring it this way so that we can see it well. So draw a laboratory. You draw the setup. First of all, before you draw, you need to know the reactants, which are actually as we know, it is made up of you produce SO2 in the lab, that's sulfur 4 oxide, by either reacting sodium sulfite or potassium sulfite with acid, either HCl or H2SO4. So the resulting thing, there will be sodium chloride, then plus H2O plus SO2, which is the gas in question. So then, but the drawing is what they want, not the weddings. So let me change to, or maybe I'll keep using my reds, no problem. Lost it. So now in that case, another way, commonly the way I prepare it also is in this way. I think I prefer this method. If you watch my video here on fountain experiment where I use SO2, HCl, many of the gases to perform astonishing fountain, what I used here was I heated copper. There should be heat here, please. I heated copper with conc H2SO4. So H2SO4, action of heat will still give you copper 2 tetrazones of A6 plus water plus C plus SO2, sorry. So whichever one, what matters is the diagrammatic representation. First, we need, you draw your round bottom flask. The round bottom flask. Remember, it's a sketch, I'm a perfect artist. Flat bottom either, so maybe to make it perfect, I go by this means. Okay. Then source of heat. And the reactant, we add the solid reactant inside. The solid reactant is probably Na2SO3. Like I told you earlier, I prefer using this one. Why? Because most of the sulfites in the lab are usually oxidized to sulfates, which will now give you SO3 gas instead of SO2 gas. That's why I prefer using copper with conc H2SO4. There will be easy oxidation there. Therefore, you have to show the liquid reactant. Let's assume we are using, yes, of course, we are using, that will be a tap. Let's use HCl this time around. So what moves in here is dilute HCl, very important. Then you have a delivery tube, which further leads to, remember your retort tripod stand should be there. Then you have your delivery tube, which goes into a vessel containing conc H2SO4 for drying of the gas. This is conical flask. There will be a support. This is kind of support. It's not the beauty of the drawing, it's your labeling that matters. Then over here you show your gas jar, where dry. So for the one that goes in, goes down, then show them what is here, and your arrow for movement. Gas moves this way. So this is conc H2SO4 for drying of the gas, and over here is your dry SO2 gas. So I think this makes it simple. So this is your gas jar, and this is the preparation source of heat. Okay, then we have settled that question. Get up here. So you can label your source of heat, although having written Bunsen burner. Then we have B part of it says mention the catalyst used for the following reaction. The reaction you see there is the reaction occurring during contact process, that is during the production of you can see during the production of H2SO4 in the laboratory by the oxidation of sulfur 4 to sulfur 6 oxide. So I have to clean this. Okay, maybe I didn't balance the question. I didn't look well, but it's not necessary. They didn't even ask the question. They just say with diagram. So my drawing is enough to speak. You get me the marks I need. Okay, the question for number 6B, if I'm okay, 6AI, sorry, if I'm right. Yeah, 6AI. 6AI says SO2 plus O2 forward backward to give you SO3. 2 is here. Then they are all gases. Gas, then 2 should be here. Okay. The question says mention the catalyst used for this following reaction. Two things are possible. So the catalyst used, either use platinum, that's platinized asbestos, platinized asbestos, platinized asbestos, or you use vanadium 5 oxide, vanadium 5 oxide. That's it. Then the next question says, and what's the effect of it? Since it's a reversible reaction, the effect of this, it doesn't shift the equilibrium to any part. So remember, catalyst has no effect on the equilibrium position. Rather, what it does is it alters the rate at which the reaction attains equilibrium. Simple. That's the answer. So the other one, which says is function, the oxide does what? Alters the rate at which the reaction attains equilibrium. Or you just say it alters the rate of both reactions. Then the next one says in the extraction, that's number 6B now. Question number 6B. 6BI. In the extraction of aluminium from bauxite, state the substance used for dissolving the ore. Simple, concentrated sodium hydroxide, or you say caustic soda, concentrated caustic soda solution. Caustic soda solution. Then the next one is composition of the mixture electrolyzed. 6BII, the mixture electrolyzed is a mixture of alumina dissolved in cryolite. So that's the substance electrolyzed. Then the anode, they say it states in the extraction of bauxite, states the anode material and give the reason why it has to be changed at interval. Simple, the anode material is use graphite rods, and the reason it needs to be changed because it needs to be changed because the oxygen liberated burns it down, because the oxygen liberated at the anode burns the graphite or burns it down. in form of carbon 4 oxide, and therefore that's oxidation reaction, which means as the electrolysis proceeds, the graphite dissolves eventually in form of CO2. Then number 6C says list 3 physical properties of an acid. Physical properties of an acid. So question 6C, I think I'm good to clean. Number 1, acids turn blue litmus paper red. Number 2, acids have sour taste. Then number 3, acids are corrosive, especially when concentrated. Yeah, so these are the physical properties of acid. Then the next one is given 0.1 mole per dm cube solution of HCl and CHCOOH, that's ethanoic acid, states and explain which of the acid solutions will have the higher electrical conductivity. Simple. The answer to CCII is that HCl will have the higher electron conductivity. That's question CII. HCl is the answer. They just say state and explain. HCl, remember, I don't need to give much account. Since you write your number where 6CII. HCl, reason because HCl is a strong electrolyte and ionizes completely in water. Because HCl is a strong electrolyte and ionizes completely in water to release more ions. Completely in water to release more ions than CH3COOH, even though their concentrations are the same. Then the other one says HCl will have the higher electrical conductivity. Simple. Then they said write an equation in each case to illustrate the behavior of HNO3 as an I acid, II oxidizing agent. So we have 6CII, question I, HNO3 as an acid. They said equation, so you just write neutralization reaction plus KOH. Make sure you balance because that will give you mark here. Balancing is very necessary in chemistry. Then what we have here, a salt is formed, which is KNO3 plus H2O. I think the equation is naturally balanced. Then II HNO3 as an oxidizing agent. You can HNO3 as an oxidizing agent. Commonly you use copper. It attacks copper metal to produce copper 2 trioxonitrate 5 plus water, yes, of course, then plus a reddish brown gas depending on the concentration. So looking at things here, we'll try putting 4 here. There should be 4 here, and then there should be 2 here because nitrogen is 2, then plus these 2 here. So I think the equation is balanced. Oxygen here is 12. This is 6 plus 4, 10 plus 4, 14. Then here is 3 times 4, which is 12. Now this is 6 plus 4, 10. And 10 plus something is wrong somewhere. But oxygen here is 12. That's just 3 times 4 is 12. So what do we do to compensate? What do we do? Okay, maybe I'll just anyone either to save my time. I'll just make this NO, and that settles it. So because it's possible when the acid is dilute, it gives us this. So that oxygen is now 4 plus 2, 6, 6 plus 6. So this is it when the HNO3 is diluted a bit. So this is oxidizing power. In this case, it oxidizes the copper to copper 2 nitrate and reduced to nitrogen 2. Yes. So that's it for question number 6. You can also you ask also with carbon, same thing. Carbon and HNO3. It oxidizes carbon to carbon 4 oxide with the release of water and also the formation of a reddish brown gas NO2. So checking the equation, if we balance it, what if you put 2 here, and put 4 here? Oxygen now is we have 6012. Then because this is required to be 4, so we have 8 plus 4 is 12. So that balances the equation. This is 2 plus 2, which is 6. 6 plus 8 is 14. Something is wrong somewhere. Wait, this 12, 3 times 4 is 12, of course. Then we have 2, 4. Then I'll still be forced to make this one. I don't know if it liberates NO. Because if it liberates NO, that balances the equation here. Because oxygen here is 8. 8 plus 4 is 12. I'm correct now. What am I even calculating? 8 plus 4 is 12. So that balances the equation. This equation is balanced. So either way. So we go to the next question, which is question number 5. Question number 5. Okay. Come here. This is 4. This is 2. This is the annoying thing when we're looking for. Okay, it's in the same page actually. So this is question number 5. So number 5 question says, let me go and replay it fully from here. State Gay-Lussac's law of combining volume. Then they give an equation, the reaction between this or that, yes. Okay. State these two uses of, as usual. Now go back. Solving notes. Gay-Lussac's law of combining volume. Question number 5. Gay-Lussac's law states that, law of combining volume states that when gases react, they do so in volumes which are in simple ratios to one another and to the product, if the product is in gaseous state, if gaseous, at constant temperature and pressure actually. So when gases react, they do so in volumes which are in simple ratio to one another and to the product, if the product is a gas. So that means that mole determines their volume. What they do in mole is what they do in volume, and what they do in volume is what they do in mole. That is it. Then the next question following it up is supposed not to have minimized this. It's not this. Not this. Okay. So the second one is calculation. The reaction below occurred between 100 cm3 of CO and was burnt in 7. The reaction below occurred when 100 cm3 of carbon dioxide was burnt in 70 cm3 of oxygen. Calculate the total volume of gas mixture in the reaction vessel at standard temperature and pressure. So the total volume of gas mixture in the reaction vessel means the residual gas. That is the gas that remains after reaction, which is equal to the volume of excess gas plus the volume of the product, if the product is actually gaseous. Though they do indicate the without even indicating the state, they have told you gas mixtures. So which means the product is also a gas. So we now go back. Bear in mind that 100 cm3 was given for CO and 70 cm3 was given for oxygen. That's what you should bear in mind. 100 cm3 for CO, 70 for oxygen. So we come here for that number 5 calculation. Remember 100 cm3 for CO, then 70 cm3 for oxygen. Then the equation of the reaction, they gave it to us, CO plus O2 to give you CO2. They balanced even the equation for us, but we can still balance it here. Put 2 here and put 2 here. This, though they didn't show us, but they say gaseous mixture. So solution, how to solve this Gay-Lussac's law of combining volume. Students often find it difficult, but when you pay rapt attention here, you won't find it difficult again. After writing the equation, what you do is bring down the mole ratio first. The moles are 2:1:2. Then come over here and just write your given volume. First step, moles, or you write mole ratio, which is what I did here. After that, you now write given volume. The volume that was given in the question, this one was given to be 100 cm3. This one was given to be 70 cm3. Nothing was given to you here, so you keep calm. Then the next step is normal reacting volume. You write normal reacting volume. What should be the normal reacting volume? You follow the ratio. The normal ratio 2:1. So if 2:1, it shows that 100:50:100. Following 2:1:2. Meaning that anytime oxygen by volume is half of carbon dioxide by volume. So if you have 2:1, 100:50, and 20:10 in that way, then after you now put minus in between. So here you now check which gas is in excess. 100 minus 100 is of course 0 cm3. Then 70 minus 50 of course is 20 cm3. Then the residual gas, the total gaseous mixture remaining, total gaseous mixture is equal to excess gas, volume of excess gas plus volume of product. So our excess gas is 20 cm3 of oxygen. It did not react. So oxygen was in excess of 20. So that 20 plus volume of this, which is the product, will give us 120 cm3. That's your final answer. So simple. We now go to the next question. So the next question there says, list 2 uses of H2SO4. Simple. H2SO4 in the laboratory is used as a drying agent. It's used to dry gases in the lab. Then it's a dehydrating agent used to dehydrate some substances. And if you use it to dehydrate sugar, you can get sugar charcoal by using concave H2SO4. Then H2SO4, many used in petroleum refining to remove pigments. Then it's used in the manufacture of fertilizer. So there are many uses of this. Manufacture of fertilizer, mainly ammonium sulfate. That's where the majority of the H2SO4 find a bigger usage. Then H2SO4 is used in the preparation of other acids, other volatile acids such as HCl, HNO3. When you treat the salts that contain nitrate 5 ion with H2SO4 on heating, it liberates HNO3. So that's the same thing. Even you use H2SO4 in pickling, that is removing rust from iron prior to electroplating. So I've settled that one. Then the next question says, give equations and reaction condition for the following conversions. How can you convert zinc carbonate to zinc oxide? Thermal decomposition by heating. Action of what? Heat. Action of heat, or you say thermal decomposition. It's the same thing. Either you say thermal decomposition. Then how do you convert zinc oxide to zinc sulfate? It's going to be by neutralization. It's going to be by neutralization. Neutralization between, or reacting it, either you write neutralization with H2SO4. Or you say you heat with concave H2SO4. Then state how each of the following can be obtained from zinc sulfate aqueous. How can you obtain solid particles of zinc sulfate from aqueous solution of zinc sulfate? Crystallization, because it's a sulfate and they are not commonly recovered by evaporation to dryness. So you use crystallization. Like this one usually comes with water crystallization, known as is in form of, I think, heptahydrate form of it. Then how can you convert zinc sulfate to zinc carbonate? By double decomposition. Double decomposition. They just say state how. Okay, you say double decomposition. You don't need to tell much story. By reacting zinc sulfate with any soluble carbonate. If you react zinc sulfate with sodium triazocarbonate 4, you get zinc carbonate straight. Then the other question says, give reasons for each of the following. That's 5. Ci, graphite is soft while diamond is hard. The reason is because the diamond crystals are tightly packed, such that the whole valence electrons in diamond crystal actually used for bonding, and this tight packaging of diamond crystal gives it its hard nature with its high density, while that of graphite have a layer structure, hexagonal layer structure, with 1 electron free out of the 4 valence electron. That gives it its flexible and a layer structure, not as strong as graphite. So simply you say because diamond have packed molecules with strong covalent bonds between each of the atoms. Out of the 4, the whole 4 is used to bond with other atoms, tightly. While in graphite, it has a layered structure and it's not tightly packed with a low density. Then sodium, reason why sodium salts cannot be prepared by double decomposition. Reason, because all salts of sodium are soluble, no exception. Take note now, all salts of sodium are soluble. I have to lay my emphasis here. All salts of sodium are soluble, no exception. So that is the reason why you cannot prepare sodium salts by double decomposition. Remember, double decomposition is used to prepare insoluble salt. Like I told you how to convert zinc sulfate to zinc carbonate. Zinc carbonate is insoluble and they use double decomposition. But there is no salt that contains sodium that don't dissolve in water. So look at these groups of salt. They all have no insoluble form. All salts of 1, sodium. 2, all salts of potassium. 3, all ammonium salts. This one, maybe the grammar don't rhyme again, but just know all sorts of ammonium or ammonium salts, all of them dissolves in water and no exception. Then another group of salts that dissolves in water, meaning all trioxonitrates, all trioxonitrate 5 salts, all trioxonitrate 5 salts, all trioxonitrate 5 salts. So these salts are all soluble in water. So no sodium salt is insoluble, no potassium salt insoluble, no ammonium salt. So from this class, if they are asking you name any insoluble salt of any soluble salt of lead, you just call the nitrate of it. Simple. So anything nitrate dissolves in water. Anything ammonium dissolves in water. So that's just by the way. Thank you. Remember to subscribe and share my videos and book for your own private classes. So that I believe that chemistry is easy. It makes life fun. The benefits of life, you better explore nature with chemistry. So be with Her Majesty, don't go far. I love you. So the next question says, why is a sodium carbonate aqueous turns? Why does it turn red litmus paper blue? Because of hydrolysis. You just say hydrolysis because it's 2 marks, but you still lay my emphasis. Because sodium triiosocarbonate 4 dissolves in water to form alkaline solution. Simple. It's a normal salt that hydrolyzes in water to form alkaline solution. It hydrolyzes in water to form alkaline, or you just say hydrolysis, or you say it hydrolyzes in water to form alkaline solution. Alkaline solution. And as an alkaline solution, we turn red litmus paper blue. Then mention 2 types of coal. We have a lignite, we have a bituminous coal, anthracite, and there are other ones I can't recall, but they say 2 types. Bituminous coal is known as soft coal. So we have the bituminous coal, then we have the anthracite. So these are the common. We have lignite also. So then the other one say name the process by which benzene is obtained from coal tar. Simple. Remember, coal tar is obtained from the destructive distillation of coal, but coal tar contains many organic compounds, even toluene, naphthalene, benzene, phenol, they are all there. So the way you separate the constituents of coal tar is by fractional distillation. So the answer to this is fractional distillation. Don't make the mistake of answering destructive distillation. Destructive distillation is the process that gets coal tar from coal. But for you to get the constituents of coal tar, you use fractional distillation. So we go to question number 4. Okay, here we go. This question number 4. Define the following terms. Enthalpy of combustion. Enthalpy of combustion means heat of combustion. Enthalpy of combustion just means heat of combustion, which is the heat change when 1 mole of a substance is completely burnt in oxygen. That is what we call enthalpy of combustion. The heat change when 1 mole of a substance is completely burnt in oxygen. So we are in question number 4. AI probably. So enthalpy of combustion also means heat of combustion is the heat change. It varies from one substance to another. Is the heat change when 1 mole of a given substance is completely burnt in oxygen. Let this color change. So that's it, enthalpy. Then another question following it, I think I say isomerism. Isomerism is the existence of 2 or more compounds. Existence of 2 or more compounds with the same molecular formula but different structural formula. That is a stereochemistry reveals that some substances, some molecules have the same formula but they have different atomic orientation. The spatial orientation of the atoms in the air are not the same, though the number and the type of atoms they have are the same. So the existence of 2 or more compounds that have the same type and number of atoms with different orientations of the atoms is what we refer to as isomers, and such existence is what we call isomerism. So existence of 2 or more compounds with the same molecular formula but different structural formula. So that's isomerism, and I just told you what it means. And the branch of chemistry that deals with that is stoichiometry. So here we go to the next question. They say classify the following oxides into acidic, basic, neutral, or amphoteric. Simple. Acidic oxides here are those ones I'm going to circle now. So acidic oxides, let me check highlighter. I think we have it here. Acidic oxides are oxides of non-metal, and we have only one here. So NO2 is an acidic oxide, and that's the only one I see here. Then basic oxides are oxides of metallic oxides. So I'm highlighting it. That is iron 3 oxide. Then they said neutral oxide. I'm highlighting that one in green. That's carbon 2 oxide is neutral. Then amphoteric, the last but not the least, is the one I'm highlighting in red. That is aluminium oxide. Then I hope these things are clear. The one in yellow is acidic oxide. The one in green is a neutral oxide. And the one in a bit dark bluish color there is a basic oxide, because it's an oxide of metal. It's a metallic oxide. Then amphoteric oxide is aluminium oxide, lead oxide, tin oxide, and also zinc oxide. So they behave as both acids and bases, but iron 3 oxide behaves as a base in the presence of acids to form salt and water. Then carbon 2 oxide of course is a neutral oxide. It has no action on litmus paper. Then nitrogen 2 oxide is an acid anhydride, and that makes it an acidic oxide. Mention 2 oxides associated with global warming. In global warming, the 2 oxides associated with global warming are actually, the chief one is CO2. We have the CO2 and the laughing gas, which is dinitrogen 2 oxide, then methane, but methane is not an oxide. They said oxide. Okay, I think ozone might contribute, but it's not oxide. So carbon 4 oxide is the main greenhouse gas, followed by nitrogen 2 oxide. Then states the main process. Remember, global warming is increase in temperature of the air due to accumulation in greenhouse gases. That is gases that absorb heat, so such as CO2 and then 2O. So states the main process involved in the industrial production of oxygen from air. In the industrial production of oxygen from air, it involves liquefaction of air and then followed by fractional distillation of liquid air. You use fractional distillation because oxygen, nitrogen, these major constituents of air have different boiling points. I think that of nitrogen is minus 196. I wouldn't accurately remember that of oxygen, but oxygen have a higher boiling point than nitrogen. So you use a fractional distillation. Then write the equation to show the action of heat on KNO3 and ammonium carbonate. Simple. KNO3, I will use the opportunity to teach you the pattern of decomposition of potassium triazonitrates. Pattern of decomposition of triazonitrates on heating. Remember, we had ammonium nitrate as an answer to one of the paper 3. That is your objective questions. Remember to watch the objective questions if you have not watched. This is for the theory. This one is already, the objectives are already on my channel here. So search for it, or you can demand for it in the comment box. So KNO3, I will answer the ones here first. When you heat this, action of heat on them will give you KNO2 plus O2. It decomposes with difficulty at high temperature to give the dioxynitrate 3, and oxygen is also an oxidizing agent. Balancing the equation, so what do we do? If you put 2 here, that's supposed to be 2 here, and that makes the equation balanced. So the same thing is applicable to sodium nitrate. So they decompose to liberate what? Oxygen with dioxynitrate 3. But ammonium carbonate, action of heat on it gives you ammonia and carbon 4 oxide. The product, when you heat this, gives you NH3 plus CO2. So balancing the equation where necessary, this should be 2 because of the nitrogen there. But what we do now to balance the hydrogen, water is formed along the process. That makes it possible. There will be formation of water also. And when water is formed, hydrogen now is it's okay. That balances the equation. So water is formed alongside the thermal decomposition of ammonium carbonate. So it will give you ammonia gas and also water with carbon 4 oxide. Yeah. Then the next question says, calculate the number of molecules in 4 grams of oxygen. The number of molecules in 4 grams of oxygen, you use your Avogadro's hypothesis. The molar mass of oxygen is that atomic gas, which is O2, which means 16 times 2, giving you 32 grams. We contain how many molecules? We have 6.02 times 10 raised to the power 23, such that 4 grams will now contain X. From our calculator department, we have that 6.0. You just say 6.02 times 10 raised to power 23, yes, times 4, then divide by 32, gives you 7.525 times 10 raised to power, that's 7.525 times 10 raised to power 22 molecules are present. List two metals that can displace ion 2 ions from each solution. You use the activity series, which means we have over here, I will remind you, have potassium, sodium, calcium, magnesium, aluminium, zinc, iron, tin, lead, hydrogen, copper, mercury, silver, and gold. The common one. So they say the one that can displace ion 2 ion. So this is ion 2. All of them above. If you write 1, 2, 3, if any of these ones above is correct, meaning potassium, sodium, calcium, magnesium, aluminium, zinc is correct. But tin, lead, copper is wrong. So the next one says during the extraction of iron in. So I guess someone understood what I just did here. So I say maybe let me highlight. If you write those ones above, cleaning. I have to undo what I've done. Okay, so these ones, yeah, correct. Then those ones below are not correct. If you list any of them, then during the extraction of iron in a blast furnace, oxygen combined with one of the raw materials to form an oxidizing agent, W. Identify W. The question is a bit complicated. Okay. The raw materials there, we have coke, we have limestone, then we have the iron ore itself in the blast furnace. So like NECO love blast furnace this year, where together with electrolysis in the objective, they asked about it so much. Okay, then coke, yes, can be oxidized. They say identify the oxidizing agent. You cannot say, oh my god, you cannot say that the oxidizing agent is carbon 2. It's not, it's CO2, because CO2, carbon dioxide is oxidizing. Of course, elements in their higher oxidation state are actually oxidizing than those of them that have low oxidation state. Then state the raw material that produced it should be the coke, which is the carbon. Then what properties are exhibited in each case when the following changes occur on exposure to air? When metallic ion converted to iron 3 oxide X HO, that's rusting. Hydrated iron 3 oxide is just what we call rusting. So they say the property, what property is exhibited is called rusting or corrosion of iron. Corrosion of iron. Then when iron 3 chloride solid is converted to iron 3 chloride aqueous on exposure to air is called deliquescence. Deliquescency. Okay, we are done with question number 5. Is it for number 4? We come to question number 3. Number 3 says, mention an element that will react with steam at red hot to produce hydrogen and an oxide of the element. You write iron. Simple. The answer to this is Fe. No long story in chemistry. Remember, answers to chemistry theories are shorter than them. Don't ever. If you see anyone demanding first class sheet in chemistry, you're writing, sorry to say, nonsense. Okay? Then they say give the formula of the oxide. Remember that when iron reacts with steam in this form, Fe plus H2O is a reversible reaction. It will give you iron 2 diiron 3, yeah, plus hydrogen gas. Yes. Let me get some things clear here. You say iron plus steam forward backward reaction will give you iron 3 diiron, okay, iron 2 diiron 3, of course, plus this. Because of this 4 we put 4 here, then 4 have affected this, then because of this 3, so solid, steam is a gas, solid and gas. So the oxide, give the formula of the oxide. Simple formula, Fe3O4. IUPAC name iron 2 diiron 3 oxide, which means out of these 3 atoms of iron here, that one exhibits oxidation of plus 2, then the 2 remaining exhibits 3, so plus 2, then plus 3 times 2 because that's the 3 atoms, gives you the 8, which will balance off with the -8 here. So state 2 reasons why an aqueous solution of potassium bromide turned reddish brown on bubbling chlorine through it. Number 1, displacement reaction, because chlorine is more reactive than bromine. Then bromine is brownish, reddish brown in color. One reason is because chlorine is more reactive than bromine and displaces it from its aqueous solution. Secondly, the color of bromine is reddish brown. Okay, write an equation for the reaction above. The equation is this. They say potassium bromide KBr plus Cl2, that's chlorine gas, will give you potassium chloride plus bromine. So balance the equation. We have to put 2 here and 2 here. So that makes it smile. Name 2 chemical industries that use limestone as raw material. Paint industry, metallurgical industry, yes. Like in furnace, blast furnace, limestone is used as source of calcium oxide and source of CO2 mainly. So that's it. You use it in paint. Yeah, I think also in whatever cement industry. Okay, yes, of course. Textile, I think might find a use there. Is there any agricultural use of limestone? Yeah, maybe as a source of alkali, a source of a lime somehow. So, but what is clear is that it's used actually in paint industry and metallurgical industry. Give one example of hygroscopic substance. One example, you can use conch H2SO4. Don't write H2SO4 without putting conch because the dilute is not. Copper 2 oxide, these are hygroscopic substances. Then copy and complete the table below. Salt to be prepared, starting material, then method of preparation. So you copy and complete. They gave you example KNO3. If you start with KOH, it's going to be neutralization. Then second one is if you want to prepare calcium chloride, the starting material is calcium carbonate. Then you react with, I would rather write there, react with dilute. The same method of preparation. Reaction with dilute acids. I wouldn't call it. I don't know, that reaction is not actually pure neutralization. Then if you want to prepare iron 3 chloride, the starting material is iron. You can start with double decomposition, no, direct combination. I think the battery to my pen is down a bit. Okay, welcome back. Sorry for the little break in transmission. I'm back. My pen is charged now. So the next question says, how do you start if you want to prepare iron 3 chloride? Then starting with iron, the method is direct combination. Direct combination. Please take note, you don't use reaction with acid, you don't use displacement reaction here. If you use displacement reaction, what is formed is iron 2 chloride, not iron 3, sorry. See what I mean here? In case you just say iron plus HC, such that iron will displace the hydrogen, but what will be formed is the lower oxidation state, then plus hydrogen. But if you want to get iron 3, you use direct combination. When iron combines directly with chlorine, it gives you iron 3 chloride. So that's how to prepare the higher chlorides. So direct combination of Fe and what? Chlorine. Then copper 2 tetrasulfate 6, if you want to prepare it starting from copper 2 oxide, it's still neutralization reaction. Then they say if you want to prepare lead 2 sulfate, your starting material is lead nitrate. Lead 2 sulfate is insoluble, then lead nitrate is soluble, therefore you use double decomposition. Okay, then we go to next one, which says in contact process, in the contact process for the manufacture of H2SO4, state how SO2 is obtained. Simple, by burning sulfur in oxygen, in the presence of oxygen, and that is S plus O2 to give you SO2. That is how to produce the sulfur 4 oxide, burning sulfur in oxygen. Then write an equation for the reaction that takes place in the catalyst chamber. We have the absorption chamber. I think I've forgotten the other one. Then the catalyst chamber. The catalyst chamber is the chamber where there is oxidation of SO2. We have written that equation before, SO2 to SO3 by atmospheric air pumping in oxygen into it. Is a reversible reaction. So which means the conditions should be very, very controlled here to ensure that the forward reaction is favored here. If not, one might see and unwanted reactions. Okay, still okay. So simple. They say write the equation. You write the equation. They have written it for yourself. I think in question number 6. That's the 6B or so. Forward, backward, SO3. You write gas. Remember to V2O5. That's vanadium 5 oxide should be present as the catalyst. So SO2 plus O2 forward, backward, SO3, 2 here, 2 here. Balance the equation because that is what will give you mark. Then remember to write V2O5, vanadium 5 oxide. Then give 2 steps required to convert sulfur of 4 oxide to the acid. The 2 steps is that number 1 is to oxidize it to first oxidize it to SO3, oxidation of SO2 to SO3, then dissolving, though you don't dissolve it direct, dissolving the resulting SO3 in water, but in actual sense you don't dissolve. So I suggest you tell the marker by dissolving the SO2 in concentrated H2SO4, also existing a spray of H2SO4 to give you oleum. So the oleum now should now be further treated with water. So the oleum will be now diluted with water to give you the required concentration of the acid you want to give you now H2SO4. So that's it. Then the next one says calculate the mass of thing that would, let me clean off all this. So calculate the mass of a thing that would be deposited from molten tin to salt if a steady current of 1.5 amperes was supplied for 2 hours. This is your Faraday law, first law. You just write tin, thank God they say tin to salt. So you write the half cell equation, which is actually, okay, let me go back to my solving board. We will memorize that 1.5 amperes was produced, was provided in 2 hours, 1.5 amperes in 2 hours. .5 amperes in 2 hours. So these are the figures we will work with. Okay, so the ion there is tin 2. The half cell equation there, or redox equation, should be Sn, which means 2 Faraday is required to liberate 1 mole of Sn, and that is 2 times 96,500 will liberate 119 grams, because the molar mass of tin is 119 grams. Therefore you keep it and go for the quantity provided, which is Q equals IT. Then the I that was given to us was actually 2 hours, if I can remember correctly, to avoid making mistakes. Okay, 2 hours and 1.5 amperes. Okay, the current provided, current is 1.5 amperes. Then time was 2 hours, which when converted gives you 2 times 60 times 60. That's actually 3,600 times 2. 2 times 60 times 60, 7,000. So this is giving you 7,200 seconds. Therefore Q is equals 1.5, that's IT, current times time, 7,200, which will give you 7,200 plus half of 7,200. So 1.5 times 7,200. That will give us 10,800 coulombs. So then you go back, 2 times 96,500 will give you 193,000. We're able to give us 119. What will 10,000 coulombs give? Whatever it gives is our final answer. So, and it will give us 119 119 over 193,000 times 10,800 coulombs over 1, such that we have 119 times 10,800 equals 285,200 divided by 19300 divided by 19300 to give you 6.65. So our final answer here is 6.66 grams of tin will be produced. Answer. Okay, or this is actually theory. Don't use that my cheat I used in objectives, or if you must use it, you tell the marker define your terms. That's my remit over Chaffa. So now let's see the next question. So we are done with that. So the mass of tin deposited should be 6.66. So give one difference between weak acid and between weak and strong electrolyte. Between weak and strong electrolyte. The difference is that weak electrolytes have a low electrical conductivity and strong electrolytes have high electrical conductivity. Or you say weak electrolyte dissociates partially while strong electrolyte dissociates completely in water. So we go to the next question, which is question 2 and 1. Okay, this is question number 2. States 3 postulates of kinetic theory of gases. Fine. It says that the temperature of the gas is the measure of the average kinetic energy of the gas. So the average kinetic energy of the gas shows the temperature of the gas. Then the volume occupied by the gas particles themselves is negligible compared to the volume of the container itself. Then the force of attraction between the gas molecules is negligible, meaning the size of the gas molecules to compare to their distance is a bit negligible, which means they occupy every available volume, of course. Then they say that the collision of the gas particles are perfectly elastic. Yes, collision of the gas particles are perfectly elastic. Then the gas molecules are moving constantly in a straight random motion, colliding with one another and with the walls of the container, exerting pressure. So you can mention any of these two that I've said. Then give two chemical properties that are common to both carbon 4 oxide and sulfur 4 oxide. Both are actually acid and hydrides. When dissolved in water gives you acid. Then both are that's the same thing as saying they are acidic oxide. Then they are covalent compounds, of course. They are covalent compounds. This is a chemical property similar to both of them. When you say they are gases at room temperature, is not a chemical property, of course. Then arrange the following elements in order of increasing reactivity: iron, copper, magnesium, and aluminium. So you use your activity series: potassium, sodium, calcium, magnesium, aluminium, zinc, iron, tin, lead, copper, mercury. That should be hydrogen here. Copper, mercury, silver, and gold. So in this case, we have from here copper. They said in increasing reactivity. So simple: copper from copper to okay, you have copper there, so let's use symbols so that it will be faster. So from the activity series, you have that copper is very low there, so they say increasing order. So copper less reactive. After copper we have iron, of course, less reactive than iron less reactive than aluminium less reactive than magnesium. So that's the correct arrangement, which means magnesium is the most reactive. Then which of the elements in AII reacts with sodium hydroxide to give hydrogen? Simple: aluminium does that. So you can watch my video here, how to fill balloon with a chemical reaction, for you to appreciate the reaction of aluminium with sodium hydroxide. Then what is activation energy? Activation energy is the energy barrier that must be overcome before reactant particles are converted to product particles. That is the minimum amount of energy that must be supplied so that reactant particles are converted to product particles. In other words, the energy that is enough to generate effective collision, converting the bonds in reactants to the bonds in products. Then what is the effect of catalyst on activation energy? Catalyst alters the activation energy. It either raises it or lowers it. So we have positive and negative catalyst. So it has the effect on the activation energy. It is either bringing it lower. When it brings it lower, it facilitates the rate. When it takes it higher, it slows the rate of the reaction. Number BII, mention the catalyst used in hydrogenation. Nickel is used in hydrogenation. Platinum can also be used in hydrogenation. Then name the products obtained by passing CO2 into sodium hydroxide. When they just say passing CO2 into sodium hydroxide, the product obtained is a kind of neutralization reaction because CO2 is an acid anhydride. They say product plus CO2. So the products that will be obtained here are, we have to, a salt need to be formed, which is sodium triisocarbonate 4 plus water. So these are the products obtained. We put 2 here. So, but they are not required. We are not required to write the equation. Just from this, I've written. Use the highlight to tell these are the products: water and sodium triisocarbonate 4. Then state 2 chemical properties of ethanoic acid. As an acid, it neutralizes base to form salt and water. Then ethanoic acid reacts with ethanol to form esters. That is, the common ester formed, or the only ester formed when ethanoic acid reacts with ethanol, is ethyl ethanoate. So esterification reaction, then neutralization reaction. They now say write an equation for the reaction of chlorine with potassium iodide. So reaction of chlorine with potassium iodide is still displacement reaction. Under starch medium, this thing turns dark blue. So we have that what will be formed is potassium chloride plus iodine. So balance the equation. There should be 2 here and there should be 2 here. Then equation of the reaction of chlorine with zinc on heating. That is direct combination. Remember, chlorine is diatomic. The state of matter, okay, will give you mark. Please, this is aqueous, this is gas, then this is also aqueous, and this should be it should be liquid, it should be solid either. Then zinc plus this gas, this is solid, will give you zinc chloride, which will still be solid. So balance the equation. I think the equation is balanced naturally, of course. Then identify the product Q in the reaction below. Chlorine plus sodium hydroxide to give you sodium chloride plus water. Since they are written 2 here, it means that Q must have only 1 sodium and oxygen remains 1. That is sodium oxochlorate 1, otherwise known as sodium hypochlorite. The sodium oxochlorate 1 or sodium hypochlorite, which is the active ingredient in your domestic bleach. So Q is sodium oxochlorate 1, NaOCl. Remember, there are other products that may be formed. It shows that this solution is a dilute, and this chlorine, the solution is dilute, and the process is happening in cold condition. But when it is hot and concentrated, sodium triisochlorate 5 is formed, used in production of matches and other explosives. What type of bond is found in chlorine molecule? A chlorine molecule have this structure, and that is 2 nonmetals. Therefore, covalent bond is the answer. Covalent bond. Then consider the following organic compounds: propene, butane, ethanol, and ethine. Which of these is an isomer of methylpropane? Butane is an isomer of methylpropane because prop shows 3, methyl shows 1. Met, how to get it? Met 1, prop 3. 1 plus 3 is 4, and that's the but here, butane, which is 4. Then, which of these can be obtained from alkanol by dehydration? Simple, ethanol. Okay, which of these can be obtained from alkanol by dehydration? That should be propene, of course. Propene. You can prepare alkenes by dehydration of their corresponding primary alkanols, then reacts with sodium to produce hydrogen. Ethanol, of course, reacts with sodium vigorously to produce hydrogen gas, just like water. Reacts with ammonium silver trioxonitrate 5 solution, the unsaturated one with triple bond, terminal alkynes, which is there, ethine. And this is a test to distinguish triple bond from double bond. So this is it for question number 2. We move straight to question number 1, which is the last but not the least. State the properties. State 3 properties of a base. They did not say chemical, they did not say physical. So anyone you say here is accepted. So you can use bases turned red litmus paper blue. You use the acronym BRB. Bases turned red litmus paper blue. Then bases are corrosive when concentrated and in solid form. Then bases react with acids to form salt and water. Then the same base have a bitter taste. So you can write any three out of these things I've said. Then outline the steps involved in the manufacture of ammonia by Haber process. First, you require mixing of nitrogen and hydrogen in the ratio of 1:3. Then passing it over finely divided iron, mixing nitrogen and hydrogen in the ratio of 1:3, then passing it over finely divided iron at the pressure of 200 atm and temperature of about 450 degrees Celsius. So then cooling the resulting product. The unreacted gases are what? Recycled. So that's it. Mixing of nitrogen gas and hydrogen gas in the ratio of 1:3. Then passing the mixture of gas over finely divided iron at 200 atm and 450 degrees Celsius. Then the mixture is cooled to remove the ammonia. Any unused gas is recycled back into the reaction chamber. Then they say define the term cracking. Cracking is actually the breaking of a compound by addition of heat. Here, answer for them. Cracking is the heating of high molecular weight hydrocarbon to produce a lower molecular weight hydrocarbon with the yield of any member of alkene which is unsaturated. So heating high molecular weight hydrocarbon to yield lower molecular weight hydrocarbon is what we call cracking. But cracking generally means breaking a compound by the application of heat. Then give one method of cracking. We have catalytic cracking, we have thermal cracking. Then we have an element represented as P has the electronic configuration 1s2, 2s2, 2p6, 3s2. Write the electronic configuration of the ion of P. First, this is actually magnesium because in total it gives you 12, which makes it magnesium. So magnesium ion have lost 2 electrons. Therefore, the electronic configuration of the magnesium ion is 1s2, 2s2 and 2p6, which means it contains 10 electrons after losing 2 out of the original 12 it had. Write the formula of each chloride. That's simple, magnesium chloride. Then state whether P, okay, they said P, don't write P here, don't write Mg here, just write P. Since they are describing it as P, please just write, what's wrong? Just write PCl2. Simple. Then state whether P is an oxidizing or a reducing agent. P is a reducing agent. Why? Because it's an electron donor. It ionizes by loss of electrons. Since it's a metal, most metals are naturally reducing agents. Why? Because they are electron donors. Remember, they ionize by loss of electron. What is electron affinity? Electron affinity is actually the energy change when one mole of a gaseous atom when a gaseous atom acquires 1 mole of electron, yes, of course, that is the energy change that accompanies the addition of electron to an atom. The energy change that accompanies the gain of electron is what we call electron affinity. Give reasons why ammonia can be involved in dative bonding. Simple, because of presence of a lone pair. It has a lone pair of electron, and that's the criteria for anything to participate. So having a lone pair of electron makes it a perfect Lewis base, because Lewis bases are electron pair donors. So it can now be involved in dative bonding. Remember, according to Lewis, acid-base reactions are actually coordinate covalent bonding, which is dative bonding. Then number D, it says x gram of a pure sample of iron 2 sulfide reacted completely with excess dilute hydrochloric acid to give 3.2 grams of iron 3 chloride according to the equation below. FeS plus this, yes, of course. Mention one method apart from heating by which the reaction can be made to proceed fast. Simple, increasing the concentration of HCl, that is using conc HCl or more concentrated HCl, then improving on the surface area of the iron 2 sulfide can also facilitate the reaction, meaning instead of using the lump, you can get it in powdered form, but iron 2 sulfide are usually gotten in lumps. But you can still improve on the rate of the reaction by affecting the size of the particles of iron 2 sulfide. Then calculate the value of X. We now go back to the question and look at it well. They say that X grams of pure sample of iron 2 here. Come to the equation. Yes. They say calculate the value of X. Okay. So meaning just to know the amount, you use your stoichiometry. According to this, I'm sure the equation is balanced. So you have 1 is to they are relating this. Okay, they say 3.2 grams of iron 3 chloride according to the equation below. I think there is a mistake here. What I saw here is iron 2, but they wrote iron 3. What will someone do here? There is a contradiction. Let me check well, but scientifically I'm not seeing. When you react iron 2 sulfide with HCl, you are going to get iron 2 chloride, which will be oxidized, of course, to iron 3. So, but they said according to the equation below. So we are expecting. I'm going to solve with reference to iron 2 chloride, please, not iron 3. So we have 1 is to 1 here. Therefore, what could they possibly mean? Since it says according to the equation below, and I'm sure it's balanced, I'm going to work with the equation and not what they wrote here, because these two things contradict. There is contradiction here. Iron 3 and what we have here is iron 2 chloride. So imagine. So the two cannot coexist actually at the same time. What do I do here? Let me solve with regard to the equation and forget the wordings. Okay, because in chemistry the wording is not a problem, it is the equation that makes us chemists. That's why I'm working with that, and no one is perfect, of course. Okay, now your reactions are needed here in this question. If you think what they mean, you tell me, but I'm going to calculate what I think is right here. Okay, so the molar mass of iron 2 chloride is actually 56 plus 71, because 35.5 times 2 is 71. 71 plus 56 is 127. Therefore, according to this, change this to mass, of course. So when I change this to mass, I got 127 grams. Then changing iron 2 sulfide to mass, we have 56 plus 32, because check the bracket here. Those figures were given to you. Sulfur is 32. They didn't even bother giving. Okay, they already gave us iron 2 sulfide is 88 without wasting time. So come back and relate. 88 grams will give you 127 grams. So what mass will eventually give us 3.2 grams? So cross multiply, you have that 127x is equal to 88 times 3.2. 88 times 3.2. 88 times 3.2. Yeah, so that x is equal to 2816. 281.6 divided by 127. Divided by 127 will give you 2.22 on the approximate. So that's the gram of the pure sample according to what they have here. So that brings this NECO 2021 paper 2 questions to an end. Thanks for being there. Please remember to watch other of my videos at Her Majesty's World Science channel. Do not only solve exam questions. The difference between me and the other thing you might think is that I do practicals. There are experiments. Please be lover of science by application, not just for exams. Albert Einstein did not become great by exam. We call them Thomas Edison. You are hearing me today, you are getting me live today, not because of I wrote exams or because you wrote exams. This is science and technology in application. Please be lover of science. Try to watch practicals. Africans, mostly Nigerians, don't watch until when it says NECO, WAEC, or JAMB, or exams in the university. Sciences are meant to be practicalized. There are entertainments here, there are DIY. So check out many videos here on this channel on human anatomy, biology. Then we have also videos on DIY. More and more are coming for your entertainment. So God bless you. Nice seeing that you are there today.
My name is Sushma Tripathi and I'm a first year medical student. We're here today to ask you to please subscribe to Sir Majesty Easy World. It has cool experiments and it makes science fun. So, subscribe! Please. I'm a medical student in St. Lucia, and I'm here to encourage you to subscribe to Sir Majesty Easy World. He does fun experiments and science missions. Please subscribe, and yeah, we'll have a good time. Intrinsic muscles of the eyeball. Different actions of the latissimus dorsi. Remember to subscribe to Sir Majesty Easy World Science channel on YouTube, and there you can find a lot of amazing videos, and yeah, they are very educative. And subscription is free. Just go online and hit on the button. About 50 videos are available for you. Educative and informative, inspiring and entertaining industrial production processes. Sir Majesty Easy World is an online school of science. No school fees, no stress. We teach the real thing. Just visit and subscribe. Thank you.
I love you. Thank you for watching.